Now in the previous session, just near the end, I was generalizing, saying that in quantum mechanics, in general, you can add pretty well any two angular momenta, and you'll get a total angular momentum L with its corresponding operators, so L hat, and L hat will be L1 hat plus L2 hat, the two respective angular momenta for your system 1 and your system 2. Now, those two systems might be two elementary particles, there might be two electrons, for example, but it could be those two angular momenta for the same one system. For example, might be an electron, single electron, and one of the angular momenta is orbital angular momentum, like the electron going around the nucleus or something, and the other angular momentum might be its spin. So you might be talking one particle with addition of orbital angular momentum and adding spin angular momentum, right? Or you might be adding two spins of two different particles. Or you might be adding two orbital angular momenta of two particles. Yeah, so in general, there are ways in quantum mechanics. It's usually high level. Now we'll do some of it in 2 chapters from now, in this text at undergrad level. But just accept there are ways to add angular momenta, and so the total angular momentum L for its operator L hat. Right? Now it'll have, in general, just as in the case when we had just one angular momentum, that one angular momentum would have little l eigenvalues for the allowed values of the angular momentum. But now this L here is now a sum. It's a sum of 2. So this little l here now is the eigenvalue of this. So you'll have L values of the summed angular momentum, little l here. And this is just thrown at you, but it'll come out of the theory when eventually you get around to doing it at grade level. These L's here range over the mod of L1 minus L2. Now L1 would be the little l value, the eigenvalue for the angular momentum of particle of system 1, and similarly for 2. So it ranges from the modulus of the difference between those two, that's the smallest value, to L1 plus L2. Okay? And so it ranges from this to this in integer steps, going up by ones at each time. So from that, if you know these two limits, you can then calculate how many different possible states are there. Well, for each L here, you'll have 2L plus 1 possible eigenvalues for the component along the z-axis of the total angular momentum here. This is the z component of that. And just analogous with theory, when we just had one system, one particle's angular momentum, the m, the eigenvalue of the z component, it can have 2L plus 1 possible values. Remember, from minus L dot 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 up to L. So 2L plus 1, and that's for. So that's your m, if you like. So in this case, m would be the eigenvalue for the z component of this, where L now is the sum. So L hat is L1 hat plus L2 hat. Right? So for a particular state of this two system you can write it this way. So it'll have a particular L, right? L is just one of the angular momentum eigenvalues for the total angular momentum, L hat, right? And for a given L, you have 2 to the L plus 1 possible components. So this m here can take on 2l plus 1 different values for each l. But your l ranges over, well, this range from this to this. Okay? So the total number of possible states will be the sum of these, where each L ranges from that to that. Now then it just becomes number theory. So I've asked you to do that for homework. So you're summing your L's from that to that, and then doubling it. And how many ones, you'll have this many times ones that you have to add to sort of be an arithmetic sum. So that's what, high school. You know how to calculate an arithmetic, a sum of numbers in the sense of a, and then a plus l, and then a plus 2l, a plus 3l, and so on. You know how to, there's a formula for that. That's from high school. So I suggest you calculate this and show that it's this. Right? So that is the total number of different states you can have for a two-system system with two parts to it, right? A two-part system, right? Okay, so that's just thrown at you, but it gives you a taste of what's coming in quantum mechanics of angular momentum. So we're saying here, it's more at grade level. Chapter 9 will talk a little bit more about it. We'll do some of this, right? And why is it? If most of it's at grade level, why is it being talked about here in undergrad level? And the answer is we need to know some of the stuff because the theory of angular momentum addition is important when discussing the physics, quantum mechanics of atoms and molecules. Like, for example, next chapter we will talk about the hydrogen atom again, but this time it won't be just the R part, the position part, spatial part. We'll also talk about the angular part, the polar angles, theta and phi. In other words, angular momentum comes into it. And if we have more than one electron, we need to start talking about addition of angular momentum. So that's the relevance, right? So we needed to understand quantum mechanics of atoms and molecules. Okay, now next topic. It's a bit marginal, a bit on the side. There's an obvious connection with angular momentum, but it's sort of tacked here on the end because it's not so highly relevant. But there is a link with angular momentum. So starting classically, if you have a charge and it's whizzing around, rotating somehow, that whizzing charge behaves sort of like a magnet. So if you put that whizzing charge in a magnetic field, it will behave as though it were a little magnet, right? The magnetic field will act on as if it were a magnet. So now magnets have what's called a magnetic moment. How can I describe that? Well, I can just throw it at you. The magnetic, now this is classic, classical mechanics, right? So we're just talking ordinary vectors. So put a little wiggle under. Now the magnetic moment, you can define it, if you like, as some constant times the angular momentum. So there's the connection. This little magnet behaving because of its angular momentum here. E is the charge that's whizzing around. M is its mass. So E over M. And now we're going to talk the electron. So this ME is the mass of the electron, and E is the charge of the electron. Right? Now this is from classical mechanics. So how can I put this? The magnetic moment gives you a measure of the strength of how strong that little whizzing charge is, acting as a magnet. So in a sense, it's how strong a magnet is it? And so the angular momentum is high. It's whizzing around pretty fast, given the mass.